right, welcome everybody. Welcome. Thank you. Thank you for staying. Thank you for coming as well. My name is Alexander Gumbach, Director in Structured Finance Ratings. This is Mercedes Conguero, Associate Director in Cyber Risk. And this is our discussion on quantum computing, opportunities, risks, and implications for enterprises. So for some reason, I was a classics major in college. And while that was a debatable choice, one experience in college, in classics, that really stuck with me was a book called Scribes and Scholars. This book was about the transmission of knowledge from the oral traditions of prehistory to the papyrus scroll of the ancient world, the codex book of the Middle Ages, and how in the Western world, at least, sometimes knowledge was trapped within the walls of the church. This continues to today, to digital innovations, right up through what you heard this morning with artificial intelligence. But what's key is that at every one of these inflection points, there was a new advance in technology that allowed us to expand and deepen our knowledge. We are perhaps at another precipice today like that with quantum computing.
Yeah, that's true, Alex. So during today, we will explore exactly that with the potential implications of quantum computing, like the risk, use cases, and even security considerations. But as Alex was saying, we are both credit rating analysts, so we are not physicists. So we are, I don't know the background of all of you, but if you're not an expert in quantum, don't be worried about the panel because we are also in that same camp. And because of that, during this intro, Alex, we will give some key takeaways that maybe will help you during the rest of the panel.
So these are just a few kind of fundamental ideas to give a little bit of context for what you're going to hear later today. So if you're experienced already, enjoy it for what it's worth. And if it's new to you, great. Well, welcome aboard. So, okay. So we know that a classical computer is built upon a bit, right? It's either on or off, a 1 or a 0. And a quantum computer uses a quantum bit or a qubit, which can be made from a variety of materials, such as an ion trapped in a magnetic field. But how is this different? So a very simplistic example is flipping a coin, right? When the coin is spinning in the air, can you say it's heads or tails, or is it kind of both, right? It's only when it lands that you can get a definite answer, right? Either heads or tails, or 1 or 0. A regular computer is a bit like that computer that has already landed, but a qubit is a bit more like that spinning coin. And scientists will call this special state of possibility superposition, when something can be in multiple states at once. Now imagine Mercedes and I have 2 coins spinning. If we did that right now, the coins would spin and they'd land wherever, whenever. But qubits are a bit different, right? They can be entangled with one another. So imagine our 2 coins are connected such that whichever way my coin spins, Mercedes spins in the exact opposite way instantly. Qubits can take advantage of these quantum realities. So, and now I know this is the point where it sounds like I'm talking about Marvel Comics multiverse of all possibilities. But the qubit can process these multiple possibilities at once. All right, so an example. In a classical computer, let's say you wanted to calculate the possible combinations of 3 bits, right? You'd have to check each combination one at a time. 0, 0, 0, 0, 0, 1, 0, 1, 0. There are 8 possible combinations, and you'd need 8 separate operations to check. In the end, you'd get one answer, right? And a quantum computer will give you that answer too, but how it gets there is a little bit different. So now we have 3 qubits instead of bits. They're entangled and in superposition. The same 8 possible combinations are there, and they're all represented simultaneously. Now specific algorithms are applied that increase and amplify the probability of finding the right answer. The algorithm is key here, right? How about one more illustration? So let's say when you all walked in here today, I handed you a blue card. But I snuck one yellow card into the deck. And now I want to find out who out there is holding that yellow card. So if we were to use a classical computer for this, right, that would be pretty straightforward. We'd have to go to each person individually and test yellow card, blue card, yellow card, blue card. That's a pretty simple algorithm, right? But we are qubits. So I would ask you to hold all of your cards up at different heights and different angles. And suddenly, every card would be out there visible at the same time. That's our superposition. Then we apply an algorithm that would encourage the yellow card to rise up just a little bit higher than the blue cards. And we keep repeating this over and over until we are most likely to find that yellow card. Now, I'm saying likely here, and because when we're thinking about quantum computers and quantum computing, we're thinking about probabilities as well. And I should say the amplification of those probabilities. Quantum computing follows the laws of nature to represent data in ways that mimic the randomness and unpredictability of the natural world. Now, this is the world that is before us, and you are about to embark on a fantastic journey. And for your guide, I give you Mercedes.
I will give you back the yellow card.
Yep.
Thank you. So now we have two fantastic panels ahead of us. The first one, we will cover more the technology and the business implications, and on the second one, we will cover more the security implications of quantum and what that means for cybersecurity. And with that, I will ask Sudeep Kesh and Jay Gambetta to join me for the first panel. So, yep.